Explain why hydrogen chloride is a gas at room temperature. Two things apply here. One is that very small molecules, very light molecules, tend to be gaseous. Very large ones tend to be solids. Take, for example, methane, ethane, propane, gaseous. Hexane, heptane, octane, nonane, decane, all liquids. And dodecane is waxy solid. They're all straight chain hydrocarbons, but the smaller, lighter ones have lower melting points and lower boiling points. And as the molecules get bigger and heavier, the melting point and the boiling point both increase. Another thing that happens is things that bond together, where you have polar attractions between molecules, that will increase those points. So octadecan 1-ol, even though octadecane is a liquid, octadecan 1-ol is a solid because it bonds together. Ethane is a gas, but ethanol is a liquid. Butane is a gas, butan 1-ol, butan 2-ol, butan 1,3-diol are liquids. And hexane's a liquid anyway. I don't think it can solidify. Oh, you can solidify hexane if you turn it into trinitrotoluene, but that's a bit of a different proposition. Hydrogen chloride, H plus Cl minus, it's not going to bond one to another, it's just going to be as is, and it's very light. Bromine, it's all about group 7 here, reacts with methane in sunlight. I did not know that. Yeah. Wow. Methyl bromine and hydrogen bromide. Table 3 shows the bond energies. Oh good. Just have to calculate. And overall energy change in the reaction. Each of these bonds has a certain amount of energy associated with it. Forming that bond releases energy. Breaking that bond requires energy. This is why when you just bounce oxygen off sugar, not a lot happens. Or wood, or sucrose, or cellulose. It's very similar chemically. If you bang them together hard enough by getting them hot, then you're putting enough energy in, and there's enough energy in the collisions to break some of those bonds and allow them to form different bonds which release more energy than was required to break the existing ones, which gives off more heat, and then you have a fire going. We have 412 in each of these four, required to break each of these four, and 193 required to break this. Carbon bromine, X, as in Wolverine, I guess. Hydrogen bromide, 366, yielded by forming this bond, an overall energy change of minus 51. Great. You have 4 of these here and 3 here, so you can ignore the 3 that haven't changed, and it's just that one that's going away and this one that we're getting. And we're breaking the 193 and getting a 366. The overall energy change is minus 51, so the 2 things on the right must add up to 51 less than the 2 things on the left. Calculate X. Why am I not surprised? 412 plus 193 minus 51 equals X plus 366. 412 plus 193 minus 366 minus 51 equals X. $188. Titanium is a transition metal. That's a sudden change. Oh yes, we're on question 8. We're no longer dealing with group 7. Isn't that nice? Titanium is extracted from titanium dioxide in a 2-stage industrial process. It's funny because it's named after Titans, but we call it titanium. Titanium dioxide, because there are 2 oxides on it, plus 2 moles of carbon, plus 2 moles of chlorine, which is a diatomic molecule. Dimer? A molecule of 2 atoms. A dimer, yes. Forming titanium tetrachloride plus 2 carbon monoxide. This sounds safe already. Stage 2, you react it with sodium to get sodium chloride. Table salt, hurrah, and pure titanium. Suggests one hazard associated with stage 1, carbon monoxide. I mean, chlorine's poisonous. So is carbon monoxide. Water must be kept away from the reaction in stage 2. I was about to say because there's sodium in it, but the question is, why would it be hazardous if water came in contact with sodium? Because it reacts very readily, very energetically, and gives off an awful lot of heat and hydrogen gas, which tends to produce a fire. Suggest why the reaction in stage 2 is carried out in an atmosphere of argon and not in air. Because if it was air, there would be oxygen around and you wouldn't get titanium, you'd get titanium dioxide again. Titanium chloride is a liquid at room temperature. Nice to know. Why would you not expect that? Because it's a very big atom. I mean, that's thallium, darling. That's not what you were looking for. You don't need to see its valence number. This isn't the element you're looking for. There it is. 22. Right. Calcium chloride. Potassium chloride is the low sodium substitute for salt. Sodium chloride is table salt. Potassium chloride is the low sodium alternative to it. Calcium chloride is a solid at room temperature. Scandium chloride, I have no idea what scandium chloride looks like. Or vanadium. Chromium chloride is a powder at room temperature. Iron chloride, powder at room temperature. Cobalt chloride, nickel chloride. Copper chloride is from memory, turns green. Is chloride green? Or is that the one that goes blue and pink? I think copper chloride is pink when wet and blue when dry, but again, solid at room temperature. Zinc chloride, I think, forms a powder, and arsenic chloride you don't want to be anywhere near. But everything else along that row, solids. Even on this row, I think aluminium chloride would be a solid. Sodium chloride's a solid. Magnesium chloride's a solid at room temperature. Titanium chloride being liquid is unexpected. Sodium displaces titanium from titanium chloride. Sodium atoms are oxidized to sodium ions in this reaction. Why is this an oxidation reaction? Because they go from neutral to +1 charge, which is an increase in charge, which is oxidation. Half equation for the oxidation reaction. Na arrow Na plus 1 electron. 1 little e minus. In stage 2, 40 kilograms of titanium chloride is added to 20 kilograms of sodium. The equation for the reaction is that. The relative atomic masses are given, so you don't need the periodic table after all. Why is it the limiting reactant? You must show your working. Oh boy. Titanium chloride, 48 plus 35.5 is 83.5 grams per mole. Sodium, and this is a balanced equation, yes, 23, hang on, titanium tetrachloride, pay attention, not titanium chloride, titanium tetrachloride. Right, so it's 4 times that much, which is 142 plus that, 190 grams per mole. 190, that would put it, oh there, osmium, thought so. Very dense stuff. Yeah. Right, that is 190 grams per mole. This is only 23 grams per mole. Now, if they want us to show our working and there are 4 marks available, they probably want you to work out that 190 divided by 40 is 4.75, and 20 divided by 23 is... Sorry, 23 divided by 20 is a little over 1, but I got that the wrong way up. 40 kilograms divided by 190 kilograms per mole is 1 over 4.75. 1 over... grief. 19 over 4 is 4/19ths of a mole. 23 is a prime number, so this is going to be ugly. It's 20 divided by 23 is 20/23 of a mole. They probably want it in decimal, but I can't be bothered. Point is, 20/23 of a mole is one heck of a lot more than 4/19ths of a mole. So you have plenty of a lot more moles of sodium. Of course, you need 4 moles of sodium per titanium tetrachloride. So you have 20/23 of a mole, but you only have enough for 5/23 of a mole of reaction, if you like. Enough to react with 5/23 of a mole of titanium tetrachloride. 5/23 is 0.21739. 4/19ths is 0.21053. So you have enough sodium to react with more titanium tetrachloride than you have. Therefore, titanium tetrachloride is the thing that runs out first. Therefore, it's the limiting factor, limiting reagent. For a stage 2 reaction, the percentage yield was 92.3%. The theoretical maximum mass was 13.5. Calculate the actual mass. 92.3% of 13.5. 92.3 over 100, in other words, or 0.923 times 13.5. This question is about acids and alkalis. I'm glad you told me that. Dilute hydrochloric acid is a strong acid. I would never have guessed this question was about acids, or alkalis at all if you hadn't told me. Explain why an acid can be described as both strong and dilute. Strong means it has a very low pH, the log base 10 of the concentration of hydrogen ions in it. And don't even start on hydrogen versus hydroxonium or any other names. Dilute means there's a low concentration of hydrogen chloride in water. It dissociates completely, so all the hydrogen becomes hydrogen ions. A 1 times 10 to the negative 3 mole per cubic decimeter, 1 millimolar to us old-fashioned people, solution of hydrochloric acid has a pH of 3.0. What is the pH of a of 1/100th the concentration? 5.0? If they're both fully dissociated. A student hydrated 25 cubic centimetre portions of dilute sulfuric acid with a 0.105 molar sodium hydroxide solution. Right, titration is using one solution, in this case sodium hydroxide, of a known molarity, concentration, in this case 0.105 molar, to exactly neutralise the other solution, in this case dilute sulfuric acid, and measuring how much it takes. This is how much is used in this row here. From this, and the known equation, which they very generously provide, you don't even have to be able to work this stuff out in your head, you can work out from these and this how many moles of this were actually used, You can use the 2 in this equation, so you should divide that by 2 to tell you how many moles of this were neutralised. That will tell you how many moles of this were in 25 cc's of your sulfuric acid sample, and you just multiply by 40 to get the concentration. As it says, calculate the concentration of the sulfuric acid. Well, the first thing to do, because he has all these different results, would be to get an average of them. 23.5 plus 21.1 plus 22.1 plus 22.15 plus 22.15. Did I get copy the numbers correctly? It looks as if I did. Equals 111 exactly. Over 5, 22.2 exactly. Isn't that nice? Isn't that convenient? Right, 22.2 cc's. There. Right, so divide by 1000 to get the number of litres. Multiply by 0.105 to get the number of moles. The average used was 0.002331 moles of sodium hydroxide. Halve it to get the number of moles of hydrogen sulfate that were neutralised, because it takes 2 moles of sodium hydroxide to neutralise 1 mole of hydrogen sulfate. 0.0011655. And then, of course, multiply by 40 to go from 25 cc's to 1 litre. Your answer is 0.04662. Use only the student's concordant results. Concordant results are those within 0.1 cc's of each other. Well, that's just those 3 then, not all of them. Always scroll down far enough to read the whole question before you start working. 66.35 over 3 equals. Right. I shouldn't zoom in quite so far. Point 0.046445. Explain why the student should use a pipette to measure the dilute sulfuric acid and a burette to measure the sodium hydroxide solution. Well, because a pipette is more accurate for getting a precise volume that you want, and a burette lets you dribble the stuff out very slowly and observe how much has been removed. Calculate the mass of sodium hydroxide in 30 cc's of a 0.105 molar solution. Bear in mind that the relative formula mass is 40. Jesus. Right, relative mass is 40, so there are 40 grams per mole. Multiply by 0.105, because that's how many moles there are per litre, tells you there are 4.2 grams per litre, and this is only 30 cc's, so multiply by 0.03 to get 0.126. End of questions. Marking scheme. Page upon page upon page of blah-de-blah-de-blah. Oh, this is actually marking scheme. Anyone from a metal carbonate like limestone, a metal hydroxide, or an alkali. Yep. Ignore base. Doesn't matter whether you call it a base metal or not. That's good. Allow a named example like limestone. Allow a correct formula rather than a word for it. Allow ammonium hydroxide, ammonium carbonate, soluble base, or ammonia. That's nice. CaNO3 2, allow it if they include the markings. Okay. Put brackets around NO3 and put the 2 afterwards. That's fine. Level 3, the method would lead to the production of a valid outcome. Was this the one where it said your method must be valid? 1.3. Where's 1.3? Describe a method to make pure dry crystals of magnesium sulfate. Yes, it wasn't that one. I do recall it. Has to actually work and be identified and logically sequenced. Would not necessarily work, but most steps are identified and it's not logically sequenced is worth 3 or 4 points, and the method would not lead to a valid outcome. But some relevant steps are identified, is worth 1 or 2 points. Wow. Okay. As I said, fairly obviously you're using magnesium oxide and sulfuric acid because, it's got to be an oxide and you want a magnesium result, and it's got to be a dilute acid and you want sulfate in the result. So of course magnesium and sulfuric. Add sulfuric acid to a beaker, warm it, add the magnesium oxide, stir. Continue adding until magnesium oxide is in excess. Yep. Filter out your magnesium oxide sludge using a filter paper and funnel to remove excess magnesium oxide. This is a whole lot of points. About how many was this thing worth? Up to 6 points for how many bullet points down there? Heat solution in an evaporating basin to crystallization point and then leave to crystallize and pat dry with filter paper. What, so you don't bake it in an oven? Alright, biologists get to use ovens. Okay, what was next? FES2 do not accept equations. What? Give the formula. We're told to give a formula and then the marking scheme says do not accept equations. Like what, S equals 2F? 26, 30, 26 must be this order. This was the number of protons, number of neutrons, number of electrons. 26, 56 minus 26, and 26. Sodium is a group or metal. 2 differences between iron and sodium. Higher melting and boiling point. It's denser, it's harder, it's stronger, it's less reactive. Yes. Iron has ions with different charges. Yep. Iron forms coloured compounds. Iron can be a catalyst. It can. You can use iron oxide as a catalyst in rocket fuel. Allow iron is magnetic. Allow specific reactions. Allow iron is less malleable and ductile. Ignore iron rusts. Yes. Fair, because they both oxidize in contact in exposure to air, just one faster than the other. Faster than the other, difference in reactivity. Allow the converse statements for sodium. I should hope so. And allow people to refer to them as group 1 metal and transition metal rather than specifically sodium and iron. Okay. Carbon is more reactive than nickel and displaces it. Yeah. Total reactance is 87, percentage atom recovery is how much you got divided by how much went in, times 100 to turn it into a percentage, 67.8%. That's just your atom efficiency. Oops. Yeah, copper, zinc and sodium chloride solution is the one that would actually produce a voltage. The reason alkaline batteries eventually die on you is that a reactant is used up. Allow the reaction stops. Allow electrolyte, electrode, ions, metal, metal hydroxide or alkali for a reactant. An electrode is used up. That'll do. I did say that. The reaction is not reversible. Also, the battery is likely to explode and burst into flames. 2H2 plus O2 to 2H2O. Allow fractions and multiples. So you could say 4H2 plus 2O2 to 4H2O, that would be correct. Or H2 plus half an O2 to half an H2O. Sorry, H2 plus half an O2 to H2O. would have been correct. Okay. 3.5. What was 3.5? Different ways to power electric cars. Oh yes. You seriously get points for saying that the time for refueling is faster than the time for recharging. Or just that a fuel cell doesn't have to be recharged. Really? And the fuel cell has the greater range. It's just the ability to read the table. Hydrogen can be renewable if made by electrolysis using renewable energy. Lithium-ion batteries can catch fire. Yeah. Produces only what no pollutants produced, but that's potentially true of both. The pollutants are produced in the generation of the energy that's used to extract the hydrogen, or in the extraction and purification of lithium. A lot of them. They release toxic chemicals on disposal. Yeah. Eventually cannot be recharged, so have a finite life. I think hydrogen fuel cell engines also have a finite life. Just how many 100-year-old cars still work? Any kind of engine, or aircraft, or anything else. Reasons why the lithium-ion battery could be judged as better. Use energy more efficiently, no Sherlock. It costs less, and it costs less to recharge than it costs to refuel. Yep. Hydrogen is often made from fossil fuels, so is not renewable. Charging points are more widely available than hydrogen filling stations, at least in some countries. Hydrogen takes up a lot of space or is difficult to store. I did mention that one because it kind of escapes. And it's highly flammable, yes. No emissions produced. Okay, yeah. Reasons why lithium-ion could be judged as better. No emissions produced. Oh, and the catalyst in the hydrogen fuel cell becomes poison, so it has a finite life. Lithium-ion batteries have a finite life. Hydrogen fuel cell engines have a finite life. Therefore, each is better than the other. That's good. BCA. Oh, this was that. Which was the model? B is plum pudding. C is the collisions. A is Mr. Bohr. I think I guessed BCA. The sum of the protons and neutrons. Mass number is the sum of protons and neutrons, and it is indeed between 69.5 and 70 for element X. Chadwick produced the evidence to show the existence of neutrons. Doesn't even say how. All four metals labelled on suitable scale on y-axis. All bars. Yeah, it's just the bar chart. Stop the bar chart. Temperature increases or temperature does not decrease. You what? 5.2. After a waste of space drawing a bar chart. Yeah. We have BCA, plum pudding, alpha particle collision, Mr. Bohr. Yada yada, Chadwick's work, that was obvious. Bar charts are boring. One reason why the conclusion is not correct is because the temperature went up, not down. Right, yes. And the questions are so boring you can't even remember answering them. And approaching 29 minutes. Whoa, 5.3 is a big one coming up at the start of the next part of this video.